Good afternoon, students. That chapter number 8, transition and inner transition elements, are completed in last lecture. But there are some index questions from this chapter we are taken in today's lecture. Started with the revision of this chapter by taking some questions. There is the one question: what is meant by? What is meant by shielding of electron? Shielding of electron in an atom. In an atom. Okay? That question: what is meant by shielding of electrons in an atom? That means we are talking about the shielding effect of electrons in an atom. That electron shielding, this electron shielding refers to the blocking of valence shell electrons. See here, this is the nucleus. There are the shells present outside the nucleus. The electrons are present nearest to the nucleus, or that shells are called the inner shells, and the electrons present in inner shells, that are called the inner electrons, and the electrons are present in outer shells are called the outer electrons. These inner electrons are act as a shield to protect the outer electrons from the nuclear attraction. To protect the outer electrons from the nuclear attraction. The electron shield refers to the blocking of valence shell electrons attraction by the nucleus due to the presence of inner shell electron. Due to the presence of inner shell electron. Right? This is the shielding of electrons in an atom. Then there is the next question: the atomic number of an element. The atomic number of an element is 90. Is this element diamagnetic or paramagnetic? Diamagnetic or paramagnetic? See, this is the property, magnetic property, right? And the element with atomic number 90. That means it is from inner transition elements. The name of this element is thorium. That is thorium 90. And the magnetic behavior of element is explained by the number of valence electrons, or the number of unpaired electrons are present in the valence. If there is a number of unpaired electrons are present, then you say that element is paramagnetic in nature. If all the electrons present in valence shell are paired, then you say the element is diamagnetic in nature. Then first you see there is the unpaired electron or not. Then first you write the electronic configuration of thorium, atomic number 90. That is radon for 50 6d2 7s2. 6d2 7s2. In this electronic configuration of element 90, that radon 4, there is no electron in 5s, there is 2 electron in 6s, and there is 2 electron in 7s. That 7s electrons are the paired, but in 6d there is the unpaired electrons. There is the 2 unpaired electrons present in 6d orbital of valence shell of element 90. So the atomic number of an element 90 is paramagnetic in nature. It is paramagnetic in nature because of the unpaired electrons present in valence shell. Clear? if there is no electron in 6d, that is 6d0 and 7s2, then radon is the noble gas, it is completely filled electronic configuration. Then 7s2, there is the paired of electron in s orbital, that means there is no unpaired electron. Then you say that atom is diamagnetic in nature. But for the thorium-90, there is 2 electron in 6d, so it is paramagnetic in nature. Then there is the next question. Iron exhibits +2 and +3 oxidation state. +2 and +3 oxidation state. Write their electronic configurations. Write their electronic configuration and which will be more stable, why? Which will be more stable and why? First, see, you read the question carefully and then start the answer. First, ion exhibits +2 and +3 oxidation states. That means ion Fe2 plus and Fe3 plus oxidation states. Then write the electronic configuration in that oxidation state. That means you write the electronic configuration of Fe2 plus and Fe3 plus. Then explain which is the more stable and why. Clear? Then first write the electronic configuration. You write first the ion. That ion atomic number is 26. You remember that because in question that atomic number is not given. So you know first the atomic number of ion. Ion is 26. Then first write the electronic configuration of ion. Argon 3d6 4s2. Argon 3d6 4s2. Then write the electronic configuration of ion 2 plus and 3 plus. Then first write Fe2 plus 2 plus. That means there is removal of 2 electrons, and that 2 electrons are removed from the large shell, not from the 3D. Then the electronic configuration of Fe2 plus is argon 3d6. Then ion 3 plus argon 3d5. There is a removal of 2 electrons from 4s and 1 electron from 3d. That is 3d5. Then there is the question which will be more stable. Then out of these two, which is the more stable? Then first observe the valence shell electrons. In ion 3 plus there is total 5 electrons in 3d, and in ion plus 2 there is total 6 electrons. And that 3d5 show the half-filled electronic configuration, which is more stable. As compared to the 3d6. So Fe3 plus is more stable. So Fe3 plus is more stable because of the half-filled electronic configuration in 3d orbital. Clear? Then in this question, if this question is asking for the 2 marks, then what is the distribution of 2 marks? That first one, Fe2 plus, there is the half mass. Then electron configuration of Fe3 plus, there is the half mass. Then remaining 1. First you write which is the most stable. You write ion in 3 plus oxidation state is more stable. You get the half mass and you explain the answer why that gets the half mass. Clear? Then there is the next question. Why salt soft? Why salt soft? Scandium 3 plus, titanium 4 plus, and vanadium 5 plus. Vanadium 5 plus are colorless. Why the salts of scandium 3 plus, titanium 4 plus, and vanadium 5 plus are colorless? See, this question coming from the property of transition metals, that is the color property of transition metals. When you see the element is colorless, that does not show the color, that does not form the colored compound, there is the first reason. If there is no presence of unpaired electron, if there is no presence of unpaired electron in d orbital, then you see the transition element is colorless. Because there is no unpaired electron, that means there is no d transition. There is the promotion of electrons from lower energy level to the higher energy level, and they absorb the energy from the visible region. If there is a presence of unpaired electron, then you see the compound formed by the transition metals are colored. But see, here you explain the colorless. That means there is no unpaired electron with this. Then first, write the electronic configuration of these three ions. Scandium 3 plus, titanium 4 plus, vanadium 5 plus. In your question, there is no given the atomic numbers. So you remember all the atomic numbers of first series of transition metals at least. Clear? Then scandium is 21, then titanium is 22, and vanadium is 23. Then, according to the 21, you write the electronic configuration of scandium first, argon, 3d1, 4s2. This is the scandium. But for the scandium 3 plus, there is a removal of these 3 electrons. So, scandium 3 plus showing the electronic configuration only argon. Only argon. Then titanium 4 plus. That titanium having the total electrons 22. Right? That scandium 21, then titanium 22, then vanadium 23. Then titanium 22, that is argon, 3d2, 4s2. Right? Then write the electronic configuration of titanium 4 plus. There is a removal of 4 electrons from this, and you get titanium 4 plus only the argon. Only the argon. Same for the vanadium. There is a removal of total 5 electrons. After that, you get only the argon core. So, argon core is the highly stable electronic configuration, and there is no unpaired electron. So, these ions are colorless because there is no unpaired electrons in their valence. Clear? That electronic configuration of these ions gets the half mass in this question. Half mass for each. Then see, there is the next question. What is the oxidation states of manganese in? What is the oxidation state of manganese in? There is a 2 ions are given. First is permanganate and second is magnet. MnO4 2 minus, and second is MnO4 minus. There is a 2 mass question, but it is from the reduced portion. because the compounds of Mn is deleted for the board exam, but that are asking for the JE or CET. Then you know from the 11th standard how to find out the oxidation state of element in ions or in compounds. Both are the polyatomic ions. Then first find in this MnO4 2 minus that Mn showing the oxidation state plus 6, because you consider the X for Mn, then X plus 4 into minus 2 equal to minus 2. Then X minus 8 equal to minus 2, you get X equal to plus 6. That minus 8 goes to that side, you get 8 minus 2, that is plus 6. Clear? Same in second, magnet ion. That manganese showing the oxidation state plus 6. Right? If this question is asking for only the 1 marks, then you write directly the oxidation state of manganese. If this question is asking for the 2 marks, then you solve that how to find out the oxidation states of manganese. Okay. Then there is the next question. This question is also from the reduced portion, but for the JE and CET students, who are taking this, balance the following reaction. Balance the following reaction. There is 2 reactions are given. The first is KMnO4 plus oxalic acid H2C2O4, and there is the formation of compounds are here, that is MnSO4 plus H2O plus K2SO4. Right? Or I think there is the CO2 is also given. First balance this reaction. That KMnO4 reacted with the oxalic acid in acidic medium. So there is the H plus ions or the sulfuric acid is given here, but in textbook there is not given the sulfuric acid. Then the correct balance reaction for this is twice KMnO4 plus thrice H2SO4 plus 5H2C2O4 gives twice MnSO4 manganese sulfate plus 8H2O plus K2SO4 plus 10CO2 plus 10CO2. This is the balance reaction for given reaction. In given reaction there is no sulfuric acid is given, but this reaction requires the sulfuric acid. Okay? Then there is a second reaction is given for the balancing. Potassium dichromate K2Cr2O7 plus 6Ki plus 7H2SO4 use 4K2SO4 plus Cr2SO4 thrice plus 7H2O plus thrice I2 plus thrice I2. This is the answer. Balance the reaction. There is only the potassium dichromate Ki and H2SO4 is given. That coefficients are not given in reaction. Right? But this is the fully balanced reaction. with the proper number of moles. Okay. Then there is the next question. Write probable electronic configuration. Write probable electronic configuration of chromium and copper. Chromium and copper. Right? Same here. In this question, there is no atomic number is given. Then you know the atomic numbers of chromium and copper. Then first one, chromium. That chromium having atomic number 24. And copper that having atomic number 29. For chromium, the atomic number is 24. And according to 24, the expected electronic configuration is argon 3d4 4s2. Argon 3d4 4s2. This is the expected. But actually, what happens? To achieve the half-filled electronic configuration in 3d orbital, the one electron from 4s gets promoted to 3d, and chromium show the observed electronic configuration argon 3d5 4s1. Argon 3d5 4s1. This is the stable electronic configuration. Right? The electronic configuration of chromium is argon 3d5 4s1. Same for the copper. The expected electronic configuration is argon 3d9 4s2. To achieve the betaine stable electronic configuration, one electron from 4s promoted to 3d, and copper show the stable electronic configuration argon 3d10 4s1. Right? This is the electronic configuration of chromium and copper. They achieve the stability of B5 and B10 configuration. Clear? Then there is the next question. Why nobelium? Why nobelium is the only actinoid? Is the only actinoid with +2 oxidation state. With +2 oxidation state. Then saying here that nobelium from the actinoid. You know the atomic number of nobelium also. That means what you remember from transition and inner transition elements? The atomic numbers of transition elements. Not for the 4 series. You only remember for the first series of D block. First series of transition elements from 21 to 30. Then you remember the electronic configuration or atomic number. At least you remember the atomic number, then you easily write the electronic configuration. That is lanthanoids and actinoids. Clear? The atomic numbers of these 3 series, at least you remember. Then see, only the nobelium is actinoid with +2 oxidation state. Then first write the nobelium having atomic number 102. To show the electronic configuration, radon core 5F14 6D0 7S2. 5F14 6D0 7S2. Right? If you write the correct electronic configuration, then from the configuration you easily write the answer of this question. that only exist in plus 2 oxidation state. Plus 2 oxidation state means there is a removal of 2 electrons from 7s and that having the 7s 0. Then to achieve the F14 configuration, that nobelium easily remove these 2 electrons and exist in plus 2 oxidation state. Okay? Nobelium is only the actinoid with plus 2 oxidation state due to the F14 electrons present in valence. Because there is only removal of 2 electrons from the 7s and you get only the 5s14. See? Then there is next question. Explain with the help of balanced chemical equation. Balanced chemical equation. Why the solution of cerium 4 acidic in nature? Cerium 4 acidic in nature. Then, first thing, explain with the help of balanced chemical equation why the solution of cerium 4 acidic in nature. Then first thing, acidic. According to the Levy's theory, the substance have a tendency to accept the electron pair is an acid. According to the Levy's theory, acid is a substance to accept pair of electrons. To accept pair of electrons. Then find out cerium 4. That cerium having the atomic number 58. That show the electronic configuration. Xenon 4, 4f1, 5d1, 6s2. Cerium, xenon, 4f1, 5d1, 6s2. Then for the cerium 4, electronic configuration is only the xenon. So you see that cerium 4 can accept the lone pair of electrons. From water molecule in its vacant orbitals. Because 5f, 5d, 4f, 5d and 6s, that are the vacant orbitals to form the complex. So you say the solution of cerium 4 is acidic in nature. That means you say the solution of cerium 4 is acidic in nature. Because that accepts the lone pair of electrons from the water. And that balanced equation is cerium 4 plus in aqueous plus NH2O to form the complex cerium H2O N. Okay? Clear? Then there is the next question. What are the stable oxidation states? What are the stable oxidation states of first plutonium, second cerium, third manganese, and fourth europium. When first stable oxidation state. Your first is the plutonium. Plutonium having atomic number 94, cerium having 58, manganese is 25, and europium is 63. Europium is 63. The atomic number of these elements are given or not given, because in textbook for this question there is no given atomic numbers of these elements. You are remember that. Then first plutonium. Plutonium showing the atomic number 94. The electronic configuration is radon 5s6 6d0 7s2. There are many unpaired electrons in the valence of plutonium, but plutonium showing the stable oxidation state +4. Besides this +4, plutonium have a tendency to show the variable oxidation state +3, +4, +5, +6 and +7. But out of these, +4 is highly stable. Then for the cerium, electronic configuration is xenon core 4f1 5d1 6s2. There are total 4 electrons in the valence of cerium. So cerium showing the 3 oxidation states +2, +3 and +4. Then manganese having the variable oxidation states are 1, 3d5, 4s2. There are total 7 electrons in the valence of manganese. So first there is a removal of these 2 electrons from the 4s to show +2, and there is total 7 electrons in the valence of manganese. Manganese show the variable stable oxidation state from +2 to +7. Then europium. That europium is atomic number 63. You write first electronic configuration xenon core 4f7 6s2. Well, see here, that europium, there is the half field in 4f orbital, right? Then there is a removal of 2 electrons from the 6s for the europium to show the +2. But europium again show the second oxidation state +3 also. That are the stable oxidation states of plutonium, cerium, manganese and europium. Clear? Then there is again one question. There is the next question. What is meant by diamagnetic and paramagnetic? Diamagnetic and paramagnetic. Give the one example. Write the one example of diamagnetic and paramagnetic from transition metals and lanthanoid metals. From transition metals and lanthanoid metals. See here. This question is asking for 3 marks. What is meant by diamagnetic and paramagnetic? Then write the one example of diamagnetic and paramagnetic from transition metals and lanthanoid metals. There are many examples of diamagnetic. Diamagnetic is less, but paramagnetic are more. Then you write any one for transition metal and lanthanoids. Then first see, what is your first question? What is mean by diamagnetic and paramagnetic? You explain diamagnetic and paramagnetic. See, when a magnetic field is applied to the substance, when the magnetic field is applied to the substance are attracted towards the applied magnetic field. The substance are attracted towards the magnetic field. It's called the paramagnetic. It's called the paramagnet that are attracted towards the magnetic field. Let's second, diamagnetic. While the ones which are repelled are called diamagnetic. The substances which are repelled by the magnetic field are called diamagnetic. Okay? Then, which is the ferromagnetic? Some substances are attracted very strongly towards the magnetic field, and these are called the ferromagnetic. But in this question, that are not as the ferromagnetic. Then see that paramagnetism and ferromagnetism that are arises due to that paramagnetism and ferromagnetism are arises due to the presence of unpaired electrons. Presence of unpaired electrons in the valence shell of elements. If there is a unpaired electrons are present, then you say that metal is paramagnetic in nature. While all electron spins are paired, then you say the compounds are diamagnetic in nature. The compounds are diamagnetic in nature. You just explain diamagnetic and paramagnetic, and then write the one example from transition metals and lanthanoid metals. For transition metals, the diamagnetic metals are, that is zinc. Zinc showing the completely filled electronic configuration. So zinc and zinc 2+. These are diamagnetic in nature. There is total paired of electrons. And paramagnetic, you write anyone from the transition metals, that is vanadium, chromium, all these.